In this next segment, we're going to look at lower bounds on approximation for certain NP-hard optimization problems. The hardness of approximation for NP-hard optimization problems is a well-studied subject in complexity theory. And we're going to show that we can prove certain results now, which are not conditional. So the typical result in the hardness of approximation is that as long as P is different from NP, it is hard to, there are no efficient algorithms that will obtain an approximation for certain NP-complete problems. I'll give a more precise statement in a moment. And what we're going to do is we're going to show categorical undefinability results, that is without the assumption that P is different from NP, but not for polynomial time, but for FPC. And as we've already said, FPC includes a very rich class of natural algorithms used for approximation. So let's start with considering a well-known problem, max 3-SAT. We're given a Boolean formula in 3CNF. So a conjunction of clauses with 3 literals per clause. Say it has n Boolean variables and m clauses. And assume that the formula is unsatisfiable. Or, I mean, it may be satisfiable. In some sense, we don't really care. But even for an unsatisfiable one, we want to look at how many of the clauses we can simultaneously satisfy. Right? This is sort of the max CSP scenario we were looking at earlier. Let's say in this formula, m star denotes the maximum number of clauses that can be satisfied simultaneously by some Boolean assignment. So m star is less than or equal to m. Now, here are the kinds of algorithmic problems we could consider. To find an assignment of values to the variables that makes m star clauses of phi true. This is the sort of thing which we, well, this is what we'd ideally like to do. We'd like to find an assignment maximizing the number of clauses that are made true. Potentially simpler problem is just determine the value of m star. Determine how many can be simultaneously satisfied. Obviously, if you can do the first, you can do the second. A third one is to just approximate m star. Okay, so clearly, if you can determine the value of m star, in particular, you can determine satisfiability. You can just check whether m star is equal to m, and that tells you whether the formula is satisfiable. For some, we say an algorithm approximates m star for some constant c if it gives you a value m prime with the guarantee that m prime is between cm star and m star. Okay. So for instance, if c was 0.9, this means the algorithm will produce a value which is guaranteed to be within 90% of the optimum value of m star. Now note, as I said, this is the problem we're really interested in. So why do we look at just determining the value of m star? Because we are talking about the hardness of the problems. We're establishing that we're going to show that this is hard to do. And that, of course, implies that this is hard to do as well. Okay. So for the purpose of establishing hardness, it does suffice to look at this. So what do we know? Well, the classic Cook-Levine theorem showing the NP completeness of satisfiability tells us that unless P equals NP, there is no polynomial time algorithm that can determine m star exactly, right? Because if you could check whether a formula is satisfiable or not, and that is impossible to do in polynomial time unless P equals NP. A couple of decades later, the PCP theorem of Aurora et al., which, the sort of foundation of the subject of hardness of approximation, and one of the most influential results in complexity theory, showed that a stronger version of this, that there is a constant strictly less than 1 right? They just show the existence of such a constant. They didn't calculate a value for it. But there is a constant strictly less than 1, says that unless p equals np, there's no polynomial time algorithm that can even approximate m star to within a factor of c. Okay, so until this point, it had been believed that maybe there were polynomial time algorithms which could get closer and closer to approximating the max 3-sat problem exactly. Okay, there could be polynomial time approximation schemes where, you know, the closer your approximation factor, maybe the higher the degree of the polynomial, but still a polynomial time algorithm for every approximation factor you could want. This showed that that was not possible unless p equals np. So under the assumption p is different from np, there is a constant. Hofstad eventually pinned down this constant exactly in the sense that he showed that for every epsilon, no matter how small, there is no polynomial time algorithm that can approximate m star to within a factor of 7/8 plus epsilon, again, unless p equals np. Why does this pin it down exactly? Because the point is that for 7/8, we can approximate m star. There's a trivial algorithm that will approximate m star to within a factor of 7/8. So that, as I said, so this pins down this value c pretty much exactly. So why 7/8? As I said, there's a trivial algorithm that will achieve 7/8, and here's a brief explanation of why. So we're looking at the problem 3-sat. So it is a conjunction of clauses. Each clause has 3 literals, right? Each literal is a variable or its negation, a Boolean variable or its negation. Now, if you look at a clause like this, there are 8 possible assignments of Boolean values to its 3 variables, and 7 of them will make it true. That's true of any clause, right? The only way to make the clause false is to make each of the 3 literals false, and there is exactly one assignment of Boolean values that will do that. So 7/8, exactly 7/8 of all Boolean assignments satisfied. Now, a simple averaging argument shows that there is an assignment of values to the Boolean variables that satisfies 7/8 of the clauses, right? I mean, just if you imagine I list all the clauses that appear in my 3-sat formula in a table. And here on the columns, I list all possible assignments of Boolean values Boolean values to the variables that appear here. Okay, so there are 2 to the n possible assignments, and I list them all. And I put a tick if that particular assignment satisfies the clause and a cross if it doesn't. And what this thing tells me is that in each row, 7/8 of the columns are ticked exactly. Okay, that means in the whole table, 7/8 of all entries are ticked. So, as I said, by a simple averaging argument, there must exist a column in which at least 7/8 of the rows are ticked, and that's an assignment that satisfies 7/8 of the clauses, at least 7/8 of the clauses. Of course, there might be an assignment that satisfies them all, but the averaging tells us that there is an assignment that satisfies at least 7/8. Okay, so to go back, the trivial algorithm that 7/8 approximates m star, just count the number of clauses m, take 7/8 of that, and report that as your m star. And that's guaranteed to give you a value which is between the actual value of n, bounded below by 7/8 of m star. Okay, maybe I should say this again. You take your instance m and you report 7/8 of m as your value of m star, and this is guaranteed to be between 7/8 of m star and m star. Right, that's the point. Now we consider a slightly different problem, the max 3 XOR problem, where again we have a Boolean formula, which is a conjunction of clauses. Each conjunction is now not the disjunction, but the exclusive OR of 3 literals. If it has n Boolean variables and m clauses, again we let m star denote the maximum number that can be simultaneously satisfied. Now, determining whether m star is equal to m can be done in polynomial time, right? Here, so given such a formula, just determining whether it is satisfiable can be done in polynomial time, because really this is just a system of equations over the 2-element field. And we can use a Gaussian elimination algorithm to determine the satisfiability. But determining the exact value of m star is hard. It's what's called max SNP complete. I haven't defined that, but never mind. Just take that as meaning it's as hard. If we could do it in polynomial time, then it would imply p equals np. So determining the exact value is hard. And what Hofstad showed was approximating it is hard to any factor better than a half. And again, achieving half is trivial, right? For exactly the same reason as before, because whenever you have an exclusive OR of 3 literals, exactly half of all assignments will make this clause true. Okay, so achieving a half is trivial. Doing anything better than a half is hard. There's no polynomial time algorithm unless p equals np. I'm going to consider another example, one which isn't of the form satisfiability. It's a graph problem. I give you a graph. In a graph, a vertex cover is simply a set of vertices such that every edge has at least one endpoint in this set. VCG denotes the size of the smallest vertex cover in G. We call that the vertex cover number of G. Now, Dinur and Safra showed in 2005 that unless p equals np, there's no polynomial time algorithm that can approximate this up to a factor of 1.36. So, because now this is a minimization rather than a maximization problem, we usually express the approximation ratio as a constant bigger than 1. If you prefer, you can take 1 over this to be the approximation factor. Kortman, Zer, and Safra improved this 1.36 to square root of 2. I say recently, it's been a couple of years now. On the other hand, there are polynomial time algorithms that can approximate the vertex cover number up to a factor of 2. In other words, they can find a vertex cover which is guaranteed to be no more than twice the size of the optimum vertex cover. There's a gap between that and this remains an open question. It's conjectured that you can't do better than 2, right? So the conjecture is that just like with the tight bounds we had for XOR SAT and 3 SAT, unless p equals np, there is no polynomial time algorithm that can approximate vertex cover up to a factor of 2 minus epsilon for any positive epsilon. Okay. I'll say a little bit about how these things are usually proved. Okay. So say that a 3CNF formula is C-satisfiable if the number of clauses that can be simultaneously satisfied is more than C times the total number of clauses. The proof of the PCP theorem, the original PCP theorem of Aurora et al., gives, for some constant C, a reduction from 3 SAT to itself, right? So it's a reduction which takes instances of, so it takes 3 CNF formulas and transforms them into sort of much larger 3 CNF formulas, which have the property that a satisfiable formula is always mapped to a satisfiable one. But an unsatisfiable one is mapped to one that's sort of highly unsatisfiable. That is not even C-satisfiable. So smaller than C proportion of the clauses can be simultaneously satisfied. And this reduction is polynomial time, right? It then follows that if you could approximate the number of satisfiable clauses to within a factor c, you could determine whether the original formula was satisfiable or not. And that we know, of course, is NP-complete by the Cook-Levine theorem. So one way of looking at this is, here we have all these satisfiable formulas. And the Cook-Levine theorem tells us that this boundary is in some sense NP-hard among all 3C and F formulas, right? It's hard to tell which side of the boundary a formula sits on. Here we have among the unsatisfiable formulas, the ones that are not even C satisfiable. That is, you can't even satisfy a C proportion of the clauses. For instance, take C to be anything bigger than 7/8. So what this theorem tells us is that any boundary you draw, which includes SAT on one side and includes all of the not C satisfiable ones on the other side, any such boundary defines a class of formulas which is NP-hard. Okay, that's the content of the theorem. So one way we put this is that the class of satisfiable formulas is not efficiently separable from ones that are not C satisfiable. There's no separation that can be efficiently decided. So the PCP theorem originally showed that there is a constant C for which this is true. And then the reductions, by further reductions, we established the hardness of other separation problems. And Hofstade's long code reductions, I'm not going to tell you what these are in this lecture. They, amplify the gap to the ones we know. Specifically in the case of 3 XOR, it's shown that if you take the class of formulas that includes the 1 minus epsilon satisfiable ones and excludes those that are not half plus epsilon satisfiable. So here, okay, let's try and draw this picture again. Now we are in the space of 3 XOR formulas. And these are the ones that are satisfiable. This boundary is easy to determine. The satisfiability problem is in polynomial time by Gaussian elimination. But take a small epsilon and just include around this all those which are nearly satisfiable. That means you can satisfy 1 minus epsilon fraction of all the clauses. And on the other hand, you include those which are less than half plus epsilon satisfiable, right? Note everything is at least 1/2 satisfiable. So this is sort of those which are just about almost as unsatisfiable as you can get. And this is saying that anything which includes all of this dotted line and excludes this, right? Any such separation is NP-hard. Okay. In particular, that dotted line itself is NP-hard to determine. We can't replace 1 minus epsilon by 1 here, precisely because satisfiability is polynomial time. Okay. In the case of max 3 sat, we can get max 3 sat by a reduction from this, but we can, in the case of max 3 sat, this 1 minus epsilon can be improved to 1, and that's called perfect completeness. Okay, and this is the statement. For any epsilon, any class 3 of CNF formulas that includes the satisfiable one and excludes the ones that are not 7/8 plus epsilon satisfiable is NP-hard to decide. What about vertex cover? Well, again, you look at the reduction from satisfiability. You take, a textbook proof of the NP completeness of vertex cover takes a 3 CNF formula with n variables and m clauses and produces a graph with 3 m vertices. You usually, take a triangle for every clause, and with the property that it has a vertex cover of twice the maximum number of satisfiable clauses in phi. Now, immediately from this, it follows using the 7/8 plus epsilon, bound on 3-sat, that now the satisfiable clauses will give you, so if m star is equal to m, then the vertex cover is the vertex cover number is at least 2/3. And if phi is not 7/8 plus epsilon satisfiable, then the vertex cover number is at most 7/12 plus epsilon of Vg. And therefore, that tells you that you can't separate these two efficiently, and therefore you can't approximate vertex cover to a ratio better than 8/7. That's the ratio between this and this. So 8/7 is not as strong an inapproximability result as the one I stated. If you start with a reduction from 3 XOR, where Hostad proves a gap between 1/2 and 1 minus epsilon, you can improve this 8/7 to 7/6. The results I mentioned of 1.36 by Dinur and Safra and square root of 2 by Kotminzer and Safra are also obtained by reductions from satisfiability, but they're much more sophisticated reductions. But it's worth pointing out that they're still gadget reductions, essentially. Okay. So now let me just tell you the results we are able to prove for FPC, and I'll give you some idea of how we prove them. For any epsilon, for any positive epsilon, there is no term of FPC. So think of this as a numeric term, which in a 3CNF formula defines a number which is guaranteed to be within 7/8 plus epsilon of m star. So to approximate m star means we're going to ask for a term of FPC, or if you will, which defines a number such that when interpreted in the formula phi, what do I mean by interpreted? We code a 3CNF formula as a relational structure on the universe of variables with 8 different ternary relations. There's a natural encoding. And in that, if you have an FPC term which defines a number, which is the number of satisfiable clauses, it's meant to be an approximation. You can't get within 7/8 of this. In the case of 3 XOR, there is no term which is guaranteed, which generates a number guaranteed to be within 1/2 plus epsilon of the maximum number of satisfiable clauses. Right? So this is exactly the kinds of hardness results we have in the classical hardness of approximability, except we don't need any assumption about P being different from NP. This is just categorically true. It's just, rather than saying there's no polynomial time algorithm, we're saying there's no term of FPC. And we can do this for vertex cover as well. We can certainly get the 1.36. We've not checked whether we can get the square root of 2, but that looks like it should be doable as well. The way we do this are by showing definability gaps. Call this new challenges for duplicator. I'll explain why in a moment. So the point is that if you have, in my picture again, you have the satisfiability, and you have in the space of XOR SAT, those which are not even 1/2 plus epsilon satisfiable, right? We say any class which includes all of the satisfiable one and excludes all this, any such class C, is not definable in FPC. In fact, it has counting width, which is linear. And note the perfect completeness, which is to say, I did not need to consider a little dotted region around this. Already, this boundary, the satisfiability boundary, we know is hard. We know that XOR SAT, 3 XOR SAT even, is not FPC definable, right? Even though it is polynomial time definable. So we can actually state perfect completeness. We didn't need to make this 1 minus epsilon over here. Then you just take the reduction from 3 XOR to 3 CNF, and that gives you the 7/8 result for 3CNF. It's impossible to separate the satisfiable 3CNFs from the ones that are not even 7/8 plus epsilon satisfiable by any class which has sublinear counting width. So our initial gap is proved for 3 XOR rather than for SAT. Okay, so in the case of the hardness of approximability, it started with SAT, and then there was this gap amplification reductions. Our initial result is proved for 3 XOR, and in some sense, this is where the work goes. So this is the restatement of the hardness of separation result. And then we extend it to 3 SAT and vertex cover by means of reductions and showed that the reductions are definable in first order logic. Really, we take known polynomial time reductions in the literature and show they can be done in first order logic. So let me tell you a little bit about how we establish the hardness for 3 XOR. So first, we consider the K-local consistency. I've alluded to this before, but now I'll define it specifically in the context of 3 XOR. Say we have a 3 XOR formula phi and some constant, some positive integer k, and consider the following game. It's a 2-player game. We call the 2 players challenger and prover, and prover is trying to show that this formula is satisfiable, and challenger is trying to challenge that. So challenger chooses a set of at most k clauses. K is the sort of resource limitation we put here. Challenger is not allowed to choose bigger sets. And prover has to give an assignment of values to the variables which satisfies all the clauses in this set. Show that this thing is consistent. This is why it's called K-local consistency. You take a subset of size k, it must be consistent. But now challenger can change the set xi plus 1 to something else. So define a new set of at most k clauses. And prover has to show that this is consistent, but in a way, without changing the variables which are in the intersection with the previous ones, right? So prover has assigned values to the variables in xi before, and those which are in the intersection can't change. Okay? So in some sense, prover has to extend the existing assignment of values to the variables to xi plus 1. But the thing is, after that, you can forget about those clauses in xi which are not in xi plus 1. So in a sense, there is a window of size at most k which challenger is allowed to move among all clauses. And at any point, just looking at that window, it has to be consistent. That's what K-local consistency means. If prover has a strategy to play forever, we say the formula is K-locally consistent. Okay. Now, I'm going to describe, I call this a CFI construction. You will see the family resemblance to the Seyfert-Ermermann construction we saw earlier on in the course. We treat a formula of 3 XOR as a system of equations over the 2-element field, in the sense that if you have a clause, let's say, for example, x XOR negation of y XOR z, when is this clause made true? Well, this is true under an assignment of values of x, y, and z if an odd number of the 3 literals is made true. Since y is negated, that's the same as saying as an even number of the variables is assigned the value true, and that's the same as saying x plus y plus z is equal to 0 in the 2-element field. Okay, so each clause becomes an equation of the form x plus y plus z equals b, for b being a constant either 0 or 1. Now, given such a system of equations, 3 variables on the left-hand side, a constant on the right, we define what I call the system CFI phi. This is going to be another system of equations. It's obtained by replacing each variable x with the 2 variables x0 and x1. And each equation of the form x plus y plus z equals b with the 8 equations where on the left I take one of the two values x0 and x1, one of the two values y0 and y1, one of the two values z0 and z1. So there are 8 possibilities. And on the right hand side, I add to b the 3 indices ij plus k, mod 2, of course. Okay, so I get 8 equations from each original equation of phi. And I call this system CFI phi. I also define what I call the homogeneous companion of phi, which is a system obtained from phi by replacing b by 0 in all the equations. And then I can take the CFI phi 0 of that. Now note, while phi 0 by definition is homogeneous, it has zeros everywhere on the right hand side, CFI phi 0 doesn't, right? In each of the 8 equations I get from an equation in phi 0, 4 of them will have 1, 4 of them will have 0 on the right hand side, just as is the case in CFI phi. And what we can prove is that if we start with a formula phi which is k locally consistent, then we cannot distinguish CFI phi from CFI phi 0 in k equivalence. This is CK equivalence. Okay. In other words, we can establish this by a k-coupled bijection game, and the argument is very much like CFI. We've replaced the assumption on tree width of the underlying graph, which we had in the case of CFI, by this k local consistency, and that lifts to a winning strategy in the k-pebble bijection game played between these two pairs of systems of equations. Now, to get a k locally consistent system, we use a sort of randomized constructions to start with a set of n variables and choose uniformly at random a collection of subsets of 3 elements. Okay. You can think of this as a bipartite graph where we have n elements on the left and m greater than n elements on the right, each of which has 3 neighbors, and so on. And you can show that with high probability this bipartite graph has expansion properties. It's essentially an expander. And we define the system of equations where each of these m subsets of size 3 corresponds to an equation, x1 plus x2 plus x3. And we choose the right-hand side to be 0, 1 by a coin flip. Right? So this is a randomized construction of a 3 XOR system. You can show with high probability this system is not satisfiable. You can't satisfy more than half the, or I should say you can't satisfy much more than half of the equations simultaneously. And the expansion properties guarantee that it is k locally consistent for a value of k which grows linearly with n. Okay. And then we show that if the formula phi is satisfiable, then CFI phi is satisfiable. That's actually not hard to show. On the other hand, if phi is not C satisfiable, then the CFI lift of it is not half plus C over 2 satisfiable. So this means that if we have a k locally consistent phi that is not half plus epsilon satisfiable, which is what I said we get by a randomized construction, then CFI phi 0 is satisfiable because phi 0, the homogeneous companion of phi, is always satisfiable. It's satisfied by the all zeros assignment. On the other hand, CFI phi itself is not 3/4 plus epsilon satisfiable. That's simply because you take C to be half plus epsilon in here, and you get 3/4 plus epsilon. Yet CFI phi and CFI phi 0 are CK equivalent. So we've shown that you can't separate satisfiable 3 XOR instances from ones that are not even not 3/4 plus epsilon satisfiable by any CK class. And since K grows linearly, you've shown that anything that separates them has linear counting width. That 3/4 can be improved to 1/2 by a sort of more careful analysis. But I won't get that. And then first order reductions, I've told you about these already. I've told you what first order reductions are. And if you have a class of unbounded counting width, which is first order reducible to another class D, then D has unbounded counting width. And if the reduction is linearly bounded, which means it takes a structure A to a structure theta A of size linear in A, then a linear lower bound on the counting width of C gives you a linear lower bound on the counting width of D. And this is what we do. We show, now having got our hardness result for 3x or max 3x or SAT, that reductions, we have first order reductions which are linearly bounded to 3 SAT and vertex cover. The reduction from 3 XOR to 3 SAT just is the utterly standard one. You take a clause of this form and you replace it by, those 4 clauses. And that translates a 1/2 unsatisfiability in the XOR to a 7/8 unsatisfiability in 3 SAT. Sorry, this doesn't give you the 7/8, I should say. We also need the long code reductions, but I haven't told you what those are, and it would take too long to get into them. And the standard reductions to vertex cover, as well as the Dinosaur reduction, are all expressible as first order reductions. So we'll take a pause here, and I will return to a final topic.